Hey, grade 12s. Here to deliver your last lesson for this unit for concept D7 in our equilibrium acids and bases unit. And the last thing we're going to look at is in looking at pH curves again. Something you should have had a quick look at when you were in Chem 20. We'll review a couple of things about that and then try to tie everything we've been talking about so far in this unit into these pH curves as a graphical way to represent what's going on with an acid-base reaction. Again, we'll be looking at using bronsted-lowry equations. We may talk about Ka, Kb, Kw, pH, pOH, all of those kinds of things. So, just to recall, for you to have a look at again, this is a pH curve. It's a really simple graph. On the y-axis, we would have pH. On the x-axis, we would usually have some sort of a volume associated with this. In this case, it tells us that this is the volume of hydrochloric acid in milliliters. And so what I want you guys to understand is a pH curve is usually related to a titration. And so our title suggests that 25 milliliters of 0.48 mole per liter sodium hydroxide titrated with, and that titrated with part indicates that whatever comes after the with is the titrant. So it's titrated with hydrochloric acid. It's easy to tell that when you have a graph in front of you because look at your starting pH. Your starting pH is, in this case, around a little under 13. And so that means we're dealing with our sample as being sodium hydroxide. And that must mean that our titrant then is hydrochloric acid because as we proceed through the titration, we see that the acidity goes down gradually, or the basicity goes down gradually, and then all of a sudden we reach our end point and we get basically an instant drop in the pH down to the range of about maybe 3 before it levels out at somewhere just below 2. This point in the middle here is what we call the equivalence point, and we would call that the equivalence point because that is where the hydroxide and hydronium ion concentrations are basically equal. And you'll notice that because we're dealing with a strong base in the form of sodium hydroxide and a strong acid in the form of hydrochloric acid, that the pH comes out to be 7. And so they neutralize each other perfectly at that point, and we end up with a pH of 7. Remember, when we're interpreting one of these titrations, what we're talking about here is that we're gradually buffering the hydroxide solution, and it has enough hydroxide ions to buffer all the way along here. What that means is that every hydronium ion that comes in from the hydrochloric acid is neutralized by the hydroxide ions, and so our pH stays relatively constant in this first leg here. But then when we hit that critical point here where there's really no more hydroxide ions left to buffer the hydronium ions, then our pH drops rapidly. And we end up then down here in a situation where there are no hydroxide ions left, and so the pH is basically that of the pH of the hydrochloric acid. These indications here, alizar in yellow, bromthymol blue, and orange 4, you'll recall to be acid-base indicators, and they're represented by a range of colors, from one color to another color, from one color to another color. I'll speak of bromthymol blue because I know what its range is roughly. Its ranges from yellow down at the bottom here to blue up at the top here. And the range is somewhere around, if I remember correctly, about 6.8 to about 7.2-ish, somewhere around there is our range. Maybe I'm a little bit off on that. Somewhere in the middle, the blend of these two colors, yellow and blue, gives us a green color. So anything above here would be blue, anything below here would be yellow, and we would have green in this range here. If you recall from last year, the way to select an acid-base indicator is by ensuring that you select something that has a color change very near the equivalence point of the reaction. And so our equivalence point is near pH 7, and so we want to have a color change somewhere around in here, aiming to sort of end up with a green color that would allow us to indicate that we're pretty darn close to that pH of 7 for our color change. So when you read a pH curve, you are reading basically a graph that is pH versus volume of the titrant. A huge amount of information is communicated from one of these graphs. From the title, you should know the chemical involved or chemicals involved. From the shape of the curve, you can determine the relative weak or strong nature of the acid or base. From the scale, and by finding the equivalence point, you can determine the concentration of the chemical being titrated if you want to go that far. A note for you, when you put a title on a graph, you must give the person reading the graph enough information to understand what the graph is all about. So what I mean by that is it's not good enough to just call the graph titration. You need to have a good title. Usually it indicates the dependent and independent variables in the reaction. So for example, titration of nitric acid by 1 mole per liter sodium hydroxide. That's a great title. It's a scientific title. It describes scientifically what is going on in that particular curve that you're looking at, or that particular graph that you're drawing. When you graph a strong acid versus a strong base, like we had in the example above, the curve has a shape which shows fairly flat sections at the start and the end. That first section, remember, I kind of called it a buffering region, and we'll talk about that more lately. And then it'll have a very steep line at the equivalence point, almost a vertical line at that point. And the pH of the equivalence point in a strong acid versus strong base is very close to 7, if not 7, because the acids and bases are, or the acid and base are similar strength. In other words, they're strong. So what I wanted to, this question here says, using some sort of distinguishing method, illustrate the buffering regions and the equivalence point. And I think we've already done that, but if you want to, you can. Let's see if I can change my color here. So this here would be our buffering region, and really we only have one buffering region on this graph. Okay, and the reason why there's only one on this graph, even though it looks like there's a similar shape at the bottom, is that there's really nothing left to buffer down here at the bottom. All that's left is water, because we've reacted the sodium or the hydroxide ions with hydronium ions, done our Bronsted-Lowry, moved a proton over, and that creates water. And then any other drops that we add from our titration are just hydronium ions at this point. So this is our buffering region, and then we indicated down here that this is our equivalence point on the graph. Okay, moving forward. If one of the chemicals is a weak acid or a weak base, and the other one is a strong version of the opposite, then the shape is somewhat different. The start and end regions, the buffer zones, are less flat. They have more of a slope to them than in our strong acid, strong base example. The equivalence point is still in the middle of that sharp rise, but that sharp rise is not as vertical as it would have been in our strong acid, strong base example. The weaker the acid or base, the gentler the upslope at the equivalence point. And if you're titrating a strong acid versus a weak base, then the equivalence point will be on the acid side of pH 7, because the strong acid tends to overrule the weak base. And vice versa, if you're doing a strong base with a weak acid, then your pH for your equivalence point will be closer to 9 or 10, so on the base side of 7, because the strong base overrules the weak acid. So this graph is a really good representation of what we're talking about here. And you kind of have to follow the curves a little bit. So the blue curve is your titration between a strong acid and a strong base. So in this case, you have a strong acid sample because the pH starts out low, and you have a strong base titrant because the pH ends up high. You'll notice that in this section here, where our equivalence point is 7 for this blue curve, our strong acid and strong base make an equivalence point of 7 there. And then our pH jumps up. You'll notice the buffering region here is relatively flat. If we looked at the titration of a weak acid with a weak base, you'll notice that the curve is this green one here. And a couple of things to point out. That region where the equivalence point is found is not nearly as steep a slope as it was in the blue curve. The other thing that you'll notice is that the buffering region has a little more slope to it than the buffering region with strong acid and base. However, because it's a weak acid and a weak base, our pH for our equivalence point still ends up to be 7 again. Now, if we were to titrate a weak acid with a strong base, then we would follow a slightly different curve. It would go here and then would kind of find its way up to here. And you'll notice that my poorly drawn vertical section here is going to wind up somewhere around here. If we wanted to even imagine it, it might have been this coming up here, with our equivalence point being greater than 7. However, if we titrated let's say a weak acid, this is, scratch that last point. So you can see that our pH is going to end up with a slightly different location for its equivalence point depending on what we're doing. Weak acid with strong base, our equivalence point will be greater than 7. If we do a strong acid with a weak base, then we would end up with this kind of curve going from here all the way up and across, and you'll notice our equivalence point is actually, it probably should be closer to around here, but that still puts us at a pH of below 7. So when we get to looking at diploma questions and things like that, you can expect to see some graphs that would ask you to interpret strong acid versus strong base, weak acid versus weak base, or what are we doing in our titration and how can we tell that without being told. And really it's looking at where your equivalence point is located and deciding whether it's greater than 7 or less than 7, and then interpreting from there. Remember, of course, that these graphs could also go like this and start out with an acid or a base, and titrate with an acid. So this is where we're going to start to talk about polyprotic, and there were some questions that we've gone through so far, particularly in your last worksheet, that mentioned polyprotic entities. Remember, when I say entity, what I'm referring to is a collective term that's going to describe an ion or an atom or a molecule or something along those lines. That's what I mean when I say entities. So in some reactions where the acid or base is polyprotic, in other words, poly meaning many, protic meaning protons, it has the ability then to gain or lose more than one proton. We're going to get a different curve in these situations. The curve actually has bumps, which represent different equivalence points as we move from the original acid and base to an intermediate acid and base to a final acid and base. Monoprotic acids and bases, like the ones we've seen here and before, only have one quote-unquote bump or equivalence point, whereas polyprotic acids and bases have 2 or more bumps or equivalence points. The number of equivalence points depends on how many protons the entity is able to gain or lose, and each bump indicates a transfer of a single proton. Note that only quantitative reactions produce detectable equivalence points in an acid-base titration. So this graph here is indicating the titration of a base with an acid, right? And I don't even need to look at the title to determine that. However, the title helps me out. Our base is going to be the carbonate ion. Don't believe me? Go and check your data booklet on pages 8 and 9, and you'll find carbonate near the bottom in the base column. And it's being titrated with a strong acid, which is hydrochloric acid. And so what we're seeing happening over here, and this is the way I kind of like to look at these equivalence points, is in this buffering region here, which you'll notice has quite a slope to it. Before we get to our first equivalence point, what we have present are carbonate ions, Okay, and those are reacting with hydronium ions. Okay, and then that's going to form an equilibrium as much as it can with hydrogen carbonate. Okay, and our hydroxide. Okay, and we're seeing a transfer of a proton in this direction. Sorry, not hydroxide, that's a mistake. Let's axe that out of there. My apologies. That should be a water molecule. And we're getting a transfer of a proton over here. Now what happens when we reach this equivalence point is our pH is still above 7, meaning that we still have some base around. And what's happened once we've reached this first equivalence point is there are no more carbonate ions left. But we're still adding hydronium ions to the solution. And so what's happening in this next buffering region here is that we've used up our supply of the carbonate ions, but we still have hydrogen carbonate ions that can buffer the hydronium ions coming from the hydrochloric acid. And so we get this equilibrium establishing, again, where our acid donates a proton to our base, and we end up with H2CO3, otherwise known as carbonic acid, and our water molecule again. And then that's at this buffering region here. Once we get past our second equivalence point, which you'll notice is quite a bit steeper, mostly because this is a weaker base than our carbonate ion, then what's going to happen is when we're down here, we've then reacted all of the hydrogen carbonate ions, and all we have left really down over here is some water, and then whatever hydronium ions that we may have added to get us past this equivalence point. So that last drop means we react the last little tiny bit of the hydrogen carbonate ions, and any of the hydronium ions left over become part of that solution, and that's why we get that massive drop in pH. So we know then that the carbonate ion is a polyprotic substance because it was able to accept one proton to turn into hydrogen carbonate and then accept another proton to turn into carbonic acid. It is no longer able to accept any more protons because it doesn't have any more negative charge. And there's no such entity out there as H3CO3+. So it's basically filled up its portion. So this is what would happen if we have the titration of a polyprotic entity. Don't forget, this can go in reverse. We could run this in reverse and start out with carbonic acid, so a pH that's low, and titrate that with a strong base like sodium hydroxide, and then we would end up transferring protons from our carbonic acid to the hydroxide. And then we would end up with hydrogen carbonate again and transfer the last proton from hydrogen carbonate to the hydroxide. So we would have a curve that would bump up twice. So it kind of looks something like that, maybe, if we were to do it in reverse. So we've talked a lot about buffers, and I think you might have a good idea of what they are right now, but I want to make some connections for you too. So a buffer refers to the combination of a weak acid with its conjugate base, or in the same solution, or a weak base with its conjugate acid. When acids or bases are added to a buffer solution, the pH changes very little, so long as the quantity added is much less than the quantities of the conjugate pair entities in the buffer. And this is simply because the acid or base in the conjugate pair is being converted to base or acid, and basically buffering the solution. Page 762, I would encourage you could pause at this point and have a quick read of it, or get back to it later. If not too much acid or base is added to the buffer capacity, if too much is added, then what we reach is what's called a buffer capacity, and that's an important term to remember. And that is the point at which the solution has no more ability to buffer. In other words, we've run out of whatever base or acid that we are using to buffer the thing we are adding to it. So we're no longer able to maintain that relatively stable pH, and so we're going to end up hitting our endpoint and our equivalence point when we're done. And so that's illustrated by something like this curve here, which starts out with an acid and is being titrated with a base. Notice first off that the pH of our equivalence point is above 7, so we are titrating a weak acid with a strong base. That makes sense because acetic acid is a weak acid, and those hydroxide ions tell us that we have a strong base. And so this is our buffering region here, and what's going on in that buffering region is that we have our weak acid in the form of acetic acid, and it is reacting with those hydroxide ions, and basically it's buffering the system, meaning that it's not allowing for a massive jump in pH because it's transferring a proton over to the hydroxide and effectively turning the hydroxide into water, and then leaving a very weakly basic acetate ion in its midst. And so that's why the pH climbs slightly but not drastically, is because we've been able to neutralize that nasty hydroxide ion into water and then leave something that is very weakly basic in its wake. All right, that is the end of this unit and the things that I have to explain to you. I hope this made sense. If it doesn't, I'll be back tomorrow and we can have a conversation about it and sort it out. Don't forget that we're looking to gear up towards doing a titration later on this week so that you can have a chance to practice some of your titration skills again. So, thanks for listening.